Okay, so this is going to be a complete change of pace here. I'm going to talk about a classical algorithm kinematic Kalman fitting work by myself.
You don't want to share your video.
You're not seeing my slides?
I'm seeing your slides. I'm not seeing you.
I'm on. I can see myself.
Okay. Interesting. Oh, I see.
Maybe there's just a lag.
Yeah, there you are. Thank you.
So the concept of kinematic fitting comes actually from the bubble chamber era. And it was actually a computerized algorithm even back in the 1970s. It was interesting reading up on this. But the concept is that you assign a particle mass while you're doing the tracking. And you basically do the analysis, in this case, for resonances, while you're doing the fitting. And that allows you to incorporate all the features of the event, for instance, the particle ID, dE by dx, the density of the dots, or the range, and all the error estimation coming from the material effects, which were important in bubble chambers. And of course, all the physical interpretation in terms of the particle identities. But what's happened in the meantime, of course, is the rise of the hegemony of geometric track fitting, where you focus on the fact that with the magnetic spectrometer, you can extract the momentum directly from geometric properties independent of particle mass. And the species interpretation, if that's important to your physics, which it often isn't, is done during an analysis phase. And for most of the high energy physics done today, especially the LHC, the impact of a mass assignment is minimal. The beta, relativistic beta for the particles of interest is very close to 1, and the detectors are light, so these geometric the material effects are small. And if you do have non-geometric effects that depend on mass, you apply those as an ancillary measurement, for instance, a d by dx or time of flight. And also in that case, the time ordering of measurements is largely irrelevant. You know that the particles are traveling away from known vertices, and you've got absolute timing information from an accelerator. So why do we want to revisit kinematic track fitting? And to do that, to explain that, I'm going to have to tell you about the experiment I work on, which is the Mu2e experiment. This is a medium scale experiment that will be running at Fermilab starting in 2024. It's a search for charged lepton flavor violation in the conversion of a muon, a negative muon, into an electron in the field of an atomic nucleus, in this case, aluminum. So our sensitivity goal is a factor of 10 to the minus 16 relative to the muon capture process, which is the most common process for a muon, which stops a negative muon stopping on an atom. And to get to that point, we need 10 to the 20th muon, so an obscene number of muons, and that's the new feature of this experiment, plus some of the geometric features, which I'm not going to go into in this talk. The experimental signature for muon to electron conversion is a single monoenergetic electron, 105 MeV, so the rest mass of the muon basically converts completely into kinetic energy. So in our case, these muons stop in a stopping target, thin foils of aluminum. They spiral into the tracker where they're detected. Most of them are captured in the aluminum and produce a number of debris products, photons, protons, etc. About 40% decay. And then, of course, these very, very, very rare few that might convert is what we're looking for. The signals are observed in this tracker and also a follow-on calorimeter. There's also an active cosmic ray veto system, which I've not shown here, but I'll talk about more later. So the key detector for our experiment is the tracker, which is 70 planes or so of straws. These straws are arranged in unusual geometry. There's a hole in the middle. These are rotated as you go along so that this hole just fills in. Well, it's still a hole, but it turns into a round hole or a dodecahedron hole. The hole is there to let most of the background particles from the residual beam pass through without generating signals. It operates in a solenoidal field, in a vacuum, and a very, very low mass environment, which is driven by the background rejection requirements. The tracking environment we have, as I mentioned, our signal track is a single particle. But on top of that is a huge amount of background hits, individual hits mostly, coming from these processes coming from the other muons, not the one we want to look at, but are there anyways. So it's about 2 gigahertz of muons giving about 100 kilohertz per straw. And there's no constraints on time or vertex that we can apply to extract this one track. The muons themselves are in a pulsed beam, but the decay time is completely random. So it's the project is extracting this track out of this haystack here. The backgrounds are, like I said, driving most of the requirements, and there are 2 principal backgrounds. One is the radiative tail of the normal muon decay, which is the Michel decay. That extends way out past the normal muon decay in vacuum in free flight due to the fact that the muon is bound to the atom. And we have to distinguish our little conversion electron signal in red here from this fast falling background that requires excellent momentum resolution, which is what drives the low mass requirement. We need better than 500 keV resolution, so less than 1% at 100 MeV. The other background are cosmic muons. These can sneak in and mimic a signal. This is one that comes in through some of our beamline elements. We have an active veto system, which is a set of scintillator paddles arranged in multi-layers around and on top of the detector. But in addition to that, we have to do in situ separation from these cosmic muons from electrons using tracking information. These muons can be coming in either in the forward or the backward direction, either one of them. We know which direction our signals are coming in from, but the backgrounds can be either. So I mentioned we have a calorimeter, which is made out of crystals, cesium iodide crystals arranged into 2 discs with the same hole. The discs are there so that we can capture a high efficiency of these electrons, even though there's a hole in the middle. The primary function of the calorimeter is this muon electron separation that I mentioned. Some of that comes from the E/P measurement. So the electrons, of course, deposit most of their energies directly and promptly, while the muons only give a fraction, only their kinetic energy. The mass, rest mass energy is released, but only after a long delay from the decay. The dominant discriminating power of the calorimeter, though, comes actually from timing. These muons at 105 MeV over C momentum are slow, and they arrive about 3 nanoseconds after you would expect a signal from an electron of the same momentum. And so that 3 nanoseconds is significant on the scale of the timing resolutions we get. And we exploit this as a form of hit in tracking while we form our tracks. So our traditional straw hits, of course, we are measuring the time through a TDC at both ends of the straw. We take the nearest one to define the time. And that measurement is, of course, proportional to the time that the particle itself arrived, passed through the straw, plus the drift time. So there's a distance that the electrons have to travel to get to the wire, and that takes a certain amount of time. And then there's a signal path that the signal induced in the straw has to make it to the end of the straw, plus electronics, et cetera, et cetera. And it's this time of closest approach that we use eventually to create a residual for our measurements. We can apply that same concept also to the calorimeter. If we consider the center of gravity of a cluster, of an electron or a muon energy cluster, defined by the direction of the crystals. The crystals integrate energy across their face, but along a given direction. And that axis allows you to define, again, a point of closest approach and a time of closest approach. And that's how we get the timing signal from the calorimeter. And we use both of these in the tracking. So this leads me to the definition then of what I'm going to call a sort of modernized concept of what a kinematic Kalman fit or track fit would be. So yes, we would choose the mass of the particle on ab initio when we start the fit. In our case, we really only care about electrons and muons, but the concept is obviously extensible. And what that really means is that we're getting 4 vectors out. We've got a Lorentz invariant way of expressing the results of the fit. But along with that, we're going to make time the key measurement, the key parameter of the fit. So it becomes a parametric variable of the fit when you're describing the trajectory of the particle as it goes through the detector. In a way, it's an extension of this because we're just taking the 3 vector position and turning it into a 4 vector. And this time that's describing the passage of the particle through the detector naturally ties together all of the sensor measurements along the track and allows us to make these correlations. We use time directly as the measurement dimension. So when we've got drift and these light sensor measures from the calorimeter, it's the natural measurement dimension. And by putting everything into the fit, all the correlations and the error propagation are handled intrinsically. And it also simplifies some of the processes. For instance, dealing with this drift is always problematic in drift chambers. By working in the time domain, we only have to deal with one function, a drift distance to time relationship, which is a more direct relationship and measurable in the lab versus a time to distance relation, which is what's used in a geometric fit. We also make the T0 an explicit track fit parameter. We have to, because in our tracks, we don't have any other constraint. It is a free parameter, individual for every single track. And we explicitly choose the time flow, so we can decide if the track is passing upstream or downstream. Basically, that's defining the hit order. So this is coded up in a package, which is actually experiment independent, called KinKal. It's on GitHub. The central class in KinKal is a track object, which owns all the results and the methods and provides accessors. The architecture is based on a processing model that was used in the Babar experiment. And there's a little bit of code that's borrowed from that. The key architectural feature of KinKal is a kinematic trajectory. So this represents the passage of the particle, at least in an ideal uniform magnetic field. Everything in the Kinkal package is templated on this in an instance of the Kinematic Trajectory Class. So that has to provide this full geometric and kinematic interface, so the position and the momentum as a function of time, etc. It also has to provide an explicit parameterization. These are 6 parameter tracks, and we're using the root methods for describing space vectors and algebraic vectors. There are 3 concrete examples of KTRAJ, of kinematic trajectories, implemented in the Kinkal package. There's an LHelix, which is a low momentum looping trajectory parameterization, I'll say more about later. An impact parameter based helix, which is more conventional for high energy physics, and actually a linear, piecewise linear trajectory where there is no geometric interpretation of momentum. It's an externally provided parameter. And the result of the fit is a piecewise collection of these simple kinematic trajectory objects, time ordered to represent the true passage of the particle, including scattering. So this low energy or looping helix parameterization was actually presented at the very first CTD conference. This is a slide that I've slightly updated from there, but I'm not going to go into it here, but it's just a connection to the past. It's a natural way of representing low energy particles that see multiple loops in the detector. So the fit implementation of KinKal is based on a processing model where what happens to the track is described as a time-ordered sequence of effects with a base class for representing those. The dedicated subclasses represent specific physical processes. For instance, a hit is, or a measurement is represented as a KKHit. Material effects from a particle crossing a piece of material is its own subclass, and same for magnetic field distortions. Each instance of one of these classes represents a discrete physical process, something that happened in the detector. These objects all implement a standard interface, which is directly related to the Kalman filtering, processing, which is akin to filtering, appending, which is akin to smoothing, and then updating. And I'll say more about that later. This is a critical component in getting a real fit working. The fit is performed trivially by basically iterating through the effects. The state of the fit is just processed and appended to or updated by each effect object as it passes through. And these effect object classes are really just wrappers. They implement the Kalman machinery, but the actual detailed content describing physical effects and such is done through owned or shared objects that they reference, such as a hit for the hit, KKHit, and a material crossing for the KKMat. And I'll say more about those. So the hit, for instance, the actual hit representation in the Kinkal package is a time hit or a track hit. Its job is to provide a residual, which is just a value, a variance, and a derivative whose dimensions can be either time or space. There's no specification. It's implicitly defined by the derivatives. So its impact on the track fit is defined by these derivatives. It makes heavy use, the implementations we provide make heavy use of time or position of closest approach functions, which compute these POCA, TOCA, and DOCA values between a given KTRAJ. They're all specializations of these different templates to provide what you need for a given one of these KTRAJ instances. The Kinkal package provides two fully implemented hits, these straw hits and callow hits, but the concept is extensible. The material effects are, again, there's a KKMat processing, but the material crossing representation is a specific class of itself. We provide a straw gas and a straw, a straw model of material for Kinkal as it exists today, which models both the effect of the particle passing through gas and through the walls, which change both the energy and scatter the particle direction. There are also magnetic field effects that need to be taken into account. This on the right is a graph projections of the model of the Mu2e magnetic field with in the range where we do precision tracking, it's a plus minus 2% variation that depends also on your position. These are important on the scale of the resolution that we need to achieve, and so they have to be corrected for. The parameterization, of course, assumes a constant field, so the way that this is handled is by integrating the effect of the difference between the field that you actually have and the field that you assume to get the change in momentum and then applying that directly to the parameters. This is, again, the same concept as was developed originally in Babar. So fit iteration is critical to get correct fit results because the initial parameters and the initial inputs are often inaccurate. This affects both the linearization. So the Kalman fits we execute are actually extended Kalman fits. They're linearizations of nonlinear equations, and starting from the wrong location, the original values, gives you the wrong derivatives and linear effects. But it's also a physical implementation detail that are incorrect often. Pattern recognition or assignment of, say, left-right hit ambiguities that need to be updated as the fit iterates. So the fit iteration is controlled by a dedicated object, which can be shared. It's a configuration object that can be used for many different tracks. It describes two nested loops. The inner loop implements the extended Kalman filter, so holding all of the physical effects, the pattern recognition, and also annealing temperature constant, recomputing derivatives until those numerically or algebraically converge. The outer loop then loops over all these physical effects, and any or all of these can be updated on any given outer loop, and this outer loop also defines the convergence criteria used to say when the inner loop is finished. And these are put together into a schedule, any number of these, and can be tuned to specific applications. So the Kinkal package includes a number of unit tests. So every single individual component of the algebra in particular needs to be validated in order to get a fit of this complexity to actually function. So these are tests, for instance, of the time or position of closest approach calculation, comparing the algebraic specializations against a numerical estimate. Again, for the scattering, you need to know how these affect
You're a little slow, Dave. You're going to have to speed up.
Okay. And material effects. I don't have that many more slides, honestly, because there's a lot of backups. The Kinkal also has in the package a toy Monte Carlo based on the Mu2e detector that allows us to test on ensembles of tracks to see what the fit properties are. An example fit on the upper left here is a printout of the configuration object describing 10 outer meta iterations with different criteria for the annealing temperature and the oscillation and convergence criteria. And this is the result of a fit for a single track printed out through the history that's stored for every track. And this is the track itself. It's about 5 milliseconds per event per track, which is comparable to the pattern recognition time for the Mu2e experiment as well. The fit in diagnostics for this toy Monte Carlo includes a tree with a lot of different parameters. These are the convergence criteria. For instance, this is the result of fitting 100,000 toy Monte Carlo 105 MeV electrons. This is the chi-squared probability. It's very flat, which is what you'd expect given that it's a toy, but it shows success. These are very boring plots of the pole parameters for all 6 of the parameters of the low energy helix representation, and these are essentially perfect Gaussians. So to get to the meat, then I mentioned position sensitivity. So a geometric fit can't really tell the difference between a downstream electron and an upstream going positron. The only difference is the hit ordering. And in our experiment, it's not explicit, but by making the kinematic fit where the timing of the hits is explicit, we can actually separate these two. So if I fit this downstream going electron as an upstream going positron, the fit criteria, the chi-squared per degree of freedom in this case, is distinguishable, allows us to resolve this degeneracy and thereby reject backgrounds. Similarly, for particle ID, in this case, I'm simulating muon particles, which are our backgrounds, and fitting them as if they were electrons. So the muons themselves have good chi-squared efficiency, but if I fit that as an electron with the wrong timing model for the mass, the wrong beta, I get a much worse chi-squared. And depending on whether I've included this calorimeter hit or not, I can reject either 70 or 90% of my muons intrinsically just from the kinematic fit. So the code is living in GitHub, as I mentioned, that uses a sconce-based build system. It works on both Linux and Mac OS. Depends on the root classes I already mentioned, the S-vector, S-matrix, and gen-vector classes. I've stolen one file out of CLHEP, but otherwise there's no CLHEP dependence. This is it. And there's documentation in the README. This is just proof that there is actually a GitHub repository with a fairly extensive README for the documentation, which we will augment in future. So in conclusion, kinematic track fitting provides advantages over geometric track fitting, especially for low momentum particles, the integration of the timing and spatial measurements. For drift chambers, those are intrinsically combined, and this is a natural way of dealing with that combination. It provides intrinsic particle ID and particle direction sensitivity and allows us to directly fit for T0 per track with all the correlations implicit. It's a well-suited package for the needs of Mu2e. The Kinkal package implements a kinematic fit with a broad range of features, and we've started to migrate the experiment to use this in Mu2e. Thank you.
Thank you. Very nice. So as usual, I'm looking for raised hands. I don't see any, so let me ask one question first. So Dave, so you're migrating to this, which means you had already implemented, I guess, geometric fitting. Is that correct?
Yeah, we have a geometric fit. We basically stole the Babar fit and added in, bags on the side to deal with these issues like the T0 propagation and simulated annealing. But this is an intrinsic.
And so can you comment on the performance? I don't know if you're limited by competing resources or not, but whether this.
Yeah, our competing, the Babar fit's very slow, half a second per track. So it's a factor, the Kinkal is a factor of 100 faster, which is expected just due to the reorganization and using faster underlying technologies like the S matrix.
Okay, but that has nothing to do with the method itself. It's just the implementation.
Not directly, no. There is an indirect connection. The meta iterations are much tighter controlled in Kinkal, and so the number of iterations needed to converge is smaller.
Okay, thanks. Andy, shoot.
Hi, very nice. Like that very much. I had one question regarding the propagation setup in your package. Is that Runge-Kutta integration for the field, or is your field sufficiently constant? So 1 or 2% you saw it inhomogeneous.
Right. It's a gradient field for reasons of flushing background particles. It's small enough that we don't need the full Runge-Kutta. A linear extrapolation or interpolation works.
Okay. If you find out you may need it, we can talk. We have the code developed for do proper time propagation for with all derivatives, also in a full Runge-Kutta formalism.
That sounds interesting. Yeah, I'd like to follow up on that. Thanks.
I don't see other hands, so thanks again, Dave.